Good afternoon and welcome back to Dr. Logic Awkwardly Does Logic. Now, it's been a very long time since we've proved any theorems about the particular logical systems that we've been discussing, and we are finally in a position to do so again today. Now, wind your way back some ways into the depths of history to when we first introduced the idea of ordered modal conjunctive normal form, OMCNF. What I'm going to prove today is that every theorem of S5, in fact, every well-formed formula, but let's focus on the theorems because they're the ones that matter. Every theorem of S5 is equivalent to a well-formed formula in ordered modal conjunctive normal form. So this is actually really easy to prove now that we've gotten all of the definitions and all of the things that we've spent the last couple of videos building up. Nevertheless, let us get up the whiteboard to see exactly what is going on. So what we are going to prove is this, that every theorem of S5 is equivalent in S5 to a well-formed formula in ordered modal conjunctive normal form. That's what we're going to prove, and here is the proof. So, given what we have just shown in, not the previous video, the one before, is that every well-formed formula in S5 is equivalent to something that is either modal degree 0 or modal degree 1, the only thing that we need to do is show that anything that is in modal degree 1 or 0 can be converted into ordered modal conjunctive normal form. So the first thing that we do is we take the result that we've already shown, reduce everything to at most modal degree 1. So what we're going to do is we're going to take an arbitrary theorem phi, and step 1, if it is not first degree or 0 degree, reduce it so that it is. And we already know that this is always going to be possible. Now, we've got something that is either first degree or 0 degree. So let's look at the different possibilities. If phi is purely propositional, then it is of 0 degree, so it has no modal operators, and it is in ordered modal conjunctive normal form by definition, because it's just the purely propositional part that is the conjunct that it is. So we can kind of ignore the purely propositional side of things. So if phi is a first degree formula, because that's the other option, because we're only looking at 0 and first degree formulas. So if it is a first degree formula, then we can say something about the particular format or structure that it has. In fact, it is going to be a truth function of well-formed formulas, each of which is itself either a 0 degree formula or is of the form box psi or diamond psi, because that's how it gets to be first degree, where psi is 0 degree. And we know that psi would have to be, because if psi also had a modal operator in it, then box psi would not be a first degree formula. It would be a degree higher than that. So we can say quite a bit about the structure of what this arbitrary theorem phi must be. Now, each one of these well-formed formulas that is either of the form box psi or diamond psi or of 0 degree, we can treat all of them individually. So treat each of these well-formed formulas as if they are atoms. So ignore the complexity of any of the internal structure in them. Treat them as atoms and then convert phi to conjunctive normal form. So we're not thinking about the modal operators, just get it into conjunctive normal form. We're thinking of this as a purely propositional formula, and we already know from many videos ago that you can always put a propositional formula into conjunctive normal form. Then use modal interchange to convert any box phi or sorry, not box or not diamond to diamond knot and box knot respectively, and the result, which we can call phi prime, will be in modal conjunctive normal form. So we are almost there because we want to get to ordered modal conjunctive normal form. So that is step 4. If this new formula phi prime is already in ordered modal conjunctive normal form, then we are done. Don't have to change what already works. But if it isn't, then by, again, a previous result in an earlier video, we can convert it from modal conjunctive normal form to ordered modal conjunctive normal form, because all that we are doing is moving the different conjuncts around into the purely propositional ones, then all of the ones that have boxes in front of them, and then all of the ones that have diamonds in front of them, and then we use the equivalence to pull the diamond out front so that we have all of the, we only have one or at most one clause that has a possibility operator. And that's it. That is literally all that we have to do to show that every theorem of S5 is equivalent to a formula in ordered modal conjunctive normal form. First, you take your formula, you reduce it to first degree if it isn't already first degree or lower. If it's purely propositional, you're done. If it's not purely propositional, then you know it's a first degree formula, so it has to have a particular type of structure and shape. Use that structure and shape to convert everything into conjunctive normal form, and then look specifically at the modal bits, do your modal interchanges as needed, then order your clauses around again, and you'll have ordered modal conjunctive normal form. Now, this is, as a proof, is both very explicit, but very abstract. And you might be thinking, okay, yes, I see that there are each of these steps that you can follow, but how does this actually work? I'll give you an example in the next video. We'll work through the conversion process, and hopefully after seeing an example, you'll be convinced that you too can do this reduction. And then you can go off and find your favorite theorems of S5 and start converting them into ordered modal conjunction normal form, because we can then do something really cool with that. So stay tuned, join me again, and we'll continue to do exciting things with S5. Until then, take care.